Thank you. Thank you very much. So following the tradition of the presenters, I should thank the organizers for letting me to speak here. Uh, it's kind of, I like feeling at home after spending a lot of time in this workshop. So I'll be presenting this talk, which is based on these three papers that came out last year and inspired by the paper by Jacob Armors and Akash Zhang, which came in 21 in Cypos Physics. With this beautiful collaboration, Goche, Jay, Alexas, Jean-Francois, Mayank, Derek Tingy, and Fabian. Uh, this is my outline. Why there's a need of yet another hydrodynamic formalism, which is called density frame hydrodynamics. After motivating you, then I'll go ahead to compare the density frame hydrodynamics with the QCD kinetics, BDNK, MIS in the 1+1 system. And then I'll tell about how one can incorporate the fluctuations, stochastic fluctuations, and how one can model that using Metropolis algorithm. So let me know if something is unclear or something is bothering you. Yeah, the problem with the covariant Landau-Lipschitz approach is that the diffusive current, which is spatial in the rest frame of the fluid, incorporates time derivatives in an arbitrary frame. So, and this leads to equations of motion which are second order in time, with again leading to runaway solutions. One way to cure this pathology is to promote the diffusive current or dissipative terms to have its own dynamical evolution equation, which is called Muserai-Stewart formulation, and this will then become second order gradients and introduce more parameters and transport coefficients which are second order in nature. This box here represents that in the numerical plots, in the numerical analysis, I'll only consider this one term, one extra second order transport coefficients in the MIS, so that we can compare with the density frame hydrodynamics without any problems. So more or less, most of the numerical simulations of the large collision systems in the heavy ions use music, MIS, or is one of its variants, DNMR and BRSSS. And it has been very successful, and we all know it. But there are some disadvantages in this MIS to me. Number one is complexity. So if we have more parameters, it is numerically difficult to implement. And the second is, to me, it seems that there is still a need of proper physical interpretation of non-hydrodynamical modes, which are present in MIS. So what is that physical interpretation? How much non-hydrodynamic modes are relevant to the physical observables in the heavy ion collisions? We don't know. So recently, some years back, there was a formalism which is first order in gradient, BDNK, and it incorporates all the first order gradient terms so that it can restore causality, but without fixing any frame. So here, in this conformal limit stress energy tensor, you see there are three parameters, lambda, chi, and eta. Eta is the shear viscosity, and lambda, chi are extra parameters. One can interpret lambda being, means it controls the size of the gradients to the heat flow, and chi controls the size of the gradients to the energy density. So before going back, one logical question is that which is better, the second order MIS or BDNK, or is there any numerical comparison between the MIS or BDNK, which is a first order theory? So recently there has been quite a progress in the numerical exploration of BDNK, and this is a snapshot of a energy density evolution with space for different eta over S, specific shear viscosity. The dots are MIS and BDNK, and so you can see what is happening is that the initial profile is Gaussian, and as time progresses, it moves away and forming two clumps. So this is a snapshot at around 9 Fermi or so. So for small shear, specific shear viscosity, you see that the MIS and BDNK have very well in agreement, but for the eta over S, which is much beyond than the normal QGP viscosity, you see that there are oscillations in the BGNK evolutions. These oscillations, yes, you can. This is MIS. Mueller is slightly squark second order in gradient. I mean the MI. Sorry. Okay. The dots are the MIS and the lines are the BGNKs. I'm little bit color flop. Yeah. Anyways, so it's fine, right, George? Yeah. How? Yeah, it's not an apple to apple comparison, but for this comparison, there are two things. One is conformal limit. Both MIS and BGNK are in conformal limit. The second is that tau pi. I mean, we only consider not we, but they only consider tau pi as a second order parameter in MIS, which is very small, but not too small, like for 0.3 GeV something. So I will not say that this is very direct comparison, but just to know that whether BDNK can be able to solve using the tools of MIS or not. That is the motivation. Yeah, right, right. So I agree. I agree with this. For example, uh, okay. So in MIS, the only second order parameter is tau pi for this comparison. And for BGNK, they use these values to fix the frame. So this is lambda 0 and chi 0 for this extra parameters here. This lambda and chi, which is written in terms of initial shear viscosity. This will fix the frame, and then they compared the numerics between MIS and BGNK. Yes. Yeah, that is conformal limit. I mean, the conformal form of the BGNK stress. Oh, yes, right. Okay. Yeah, so these are the values which they have took, and then they compared between MIS and BKNK. So for the small specific shear viscosity, they find a good agreement, very nice agreement between second order MIS and BKNK. But for the large eta over S, you see that there are some oscillations coming up here. And this represents two things. The first is that it incorporates second order in gradient terms in the numerical evolution when time is progressing. And then it also pushes the system out of the convergence of gradient expansion because it violates the weak energy conditions. Of course, if you wait long enough, that is around 100 Fermi or so, all these oscillations will die out and eventually match with the MIS. But at around time, which at around 9 Fermi or so, you see that there are some oscillations coming up because of this. I will speak more when I compare with density frame, but for now, I'm just showing that there has been some numerical analysis for the BGNK, and there has been some comparisons with the MIS. So we know that large collision systems have a heavy ions. Most of the numerical simulations use MIS or its variants, where fluctuations are very important. But when what happens in the small collision systems, the fluctuations are important because the number of produced particles are very less, and you cannot just neglect the fluctuations. And there has been evidence that the small systems also show collectivity, collective behavior. So hydrodynamics will still be applicable. To what regime? That is a debatable question, but we can still apply hydrodynamics, but with fluctuations incorporated. So what is our main motivation? The main motivation is to have the hydrodynamic formalism, which can incorporate the fluctuations without any problems. And we would like to describe the systems, small system physics and physics near the critical point. So that is our main goal. So let's begin here. So consider a charge in a moving fluid, which is not Lorentz invariant. So this is this, and then the Ji can be decomposed in terms of ideal advection term, Vi, the free velocity, and the diffusion term. To first order in gradients in N, this is the total, I mean, Ji can be retained. You can have only these two terms. The first term is the parallel to the velocity, and the second term is perpendicular to the velocity. Now, to obtain what is the form of d parallel and d perpendicular, that is diffusion coefficient parallel and perpendicular to velocity, let's go to the Landau frame definition. So this is a Landau frame definition, which is J mu equal to nu mu, J give mu, and then define the J0 as n, and then use the lowest order, the ideal equations of motion in this to replace the left frame time derivatives from here with the space derivatives. So whenever you see that there is del Tn, you replace it with Vi del In. And what you get is this, Ji equal to this, the full current here. So you see by comparison that d parallel is d by gamma cube, and d perpendicular is d by gamma. So gives you the non-covariant form of the equations here. And this gamma can be represented physically, meaning that d has the unit distance squared per time. So longitudinally, you see there is a separation of gamma cube with respect to the fluid at rest because of time dilation and length contraction. Yes. Yes, yes, of course. And yeah, so longitudinal diffusion coefficient is suppressed by 3 factors of gamma because of time dilation and length contraction. And the transverse diffusion coefficient is suppressed by 1 factor of gamma because of time dilation. So this is pretty nice. And this is the form of the advection diffusion equation in the density frame. This makes the equations strictly first order in time and stable, but non-covariant form. And one can also see the difference between density frame and the Landau frame by looking at the chemical potential definition. So in the density frame, chemical potential can be known if you just know J0, but in the Landau frame, you need the full J mu to understand what is chemical potential, to know the definition of chemical potential. So this is one difference between density frame and Landau frame. Yes. Generally break Lorentz invariance, right? Right. No. This is. I mean, in the density frame, this is a density frame advection diffusion equation. In the density frame, one can obtain the definition of the information of chemical potential if you just know the charge density J0. But in the Landau frame, which is the usual fluid dynamical frame, you have to know both J0 and Ji to obtain the information of chemical potential. So this is just a difference between density frame and the Landau frame hydrodynamics. Mhm. Yes, this is our definition of chemical potential. No, okay. What I'm saying is that chemical potential is the same, but to obtain the definition, to obtain the information of your chemical potential of a system, that depends how many variables you need to know. It's a lab frame, yeah, it's a lab frame quantity. Okay, so hydrodynamics, the full hydrodynamics can also be obtained in the same way. So here, the evolution variables are the energy density and the momentum density, and this will give us the definition of beta mu. And these are the equations of motion for energy density and momentum density, where this is the special stress tensor that needs to be specified. In the density frame, this Txx is written, I mean, have correction terms due to a viscous stress tensor, which is of this form. And how to obtain this is, first we need to find the derivatives of T mu with respect to beta. That is called generalized susceptibility. Then we obtain the thermodynamic susceptibility, which is the chi0 mu nu. This describes the equilibrium fluctuations of T0 mu. Then we find the inverse thermodynamic susceptibility. Now, to obtain the density frame equations of motion from the Landau frame, we redefine beta mu, where beta underlying is the Landau frame and beta mu without underlying is the density frame quantity. So we need to redefine the beta mu, which is with delta beta mu, to remove the temporal components of the viscous stress tensor. Okay. So in this process, there are many steps. Like these are just the main steps where you need some quantities. Means during the process, you need to differentiate your T mu nu with respect to beta mu, and that we call generalized susceptibility. So okay, so we, we don't need. I mean, we don't use directly this. We use the zero component, which is this the inverse thermodynamic susceptibility, which comes from here. I mean, you need to define this thermodynamic susceptibility, which is chi 0 mu nu, and yes, yes, okay, right. Means chi, I mean, directly chi mu nu rho is not used. We use chi 0 nu rho, which is the thermodynamic susceptibility. That's all. Not directly. But we need these derivatives. I mean, the derivative of T 0 nu with respect to beta rho. And then, okay, so and then we obtain the inverse thermodynamic susceptibility, which is this, in terms of sound speed and u rho, the velocity. And to obtain the density frame equation from the Landau frame, we redefine the fluid velocity to remove the temporal components of viscous stress. So in the density frame, we don't have pi 0 new components. We only have pi ij. So this shift in the beta mu is written in this form: minus chi mu nu inverse Landau frame pi 0 nu. And we see that the shift propagates into the spatial stress. And in approximating, we use this form of the derivatives with respect to Txx, with respect to T0 mu. And this frame transformation can be written in the form, in a very compact form, where we introduce kappa mu nu xx for the 1 plus 1 dimension. After that, we have to use the ideal equations of motion. So after using the ideal equations of motion, we replace the time derivatives appearing here in this pi mu nu with the space derivatives. And this gives me the kappa xxx, which was there in the 1 plus 1 form. Okay, so this is for the 1 plus 1 form, but for the 3 plus 1 form, this is not very nice looking, but still one can compute this analytically. And here, the only variables are the eta, that is shear viscosity, sound speed squared, and the zeta. There are no other parameters, no additional modes, no non-hydrodynamical modes, and no additional parameters here present. So if we have the Landau frame definitions, use the ideal equation of motion to replace the time derivatives, do the field redefinition in this form, in this way, and you will obtain the density frame equations of motion. Okay, so these are the properties of the density frame hydrodynamics. This is a hydrodynamics without underlying boost symmetry. One can easily implement the Metropolis of this, and noise can be added naturally. There are no non-hydro modes and no additional parameters. Density frame equations of motion can be derived once if one uses the ideal equations of motion. Equations are first order in time. Okay, and since we used the approximation using the ideal equation of motion, this is variant and equal. So so now I'm going to present some comparison between the density frame hydrodynamics with the other QCD kinetics and MIS. So we initialize the system with system of gluons with the Gaussian and evolve. So these are the parameters for our density frame initialization, and this is the definition of the Knudsen number. So you see that again, when I compare with the compare a Gensky frame with a big ENK for the small specific shear viscosity. This is again have a nice agreement, but as eta over S is increasing, you'll see that there is some discrepancy coming in, between Gensky frame and big ENK. Let me show you one video right here. So initially it is a Gaussian profile, and then with time, as time progresses, it moves away and form two clumps, and you'll see that when the eta over S is increasing, there are some oscillations which I was saying before appearing in the big ENK formalism, which means that it incorporates second order ingredient terms in the numerical evolution. And eventually, when eta over S is much, much larger, then this big ENK code crashes out. Yeah, so this you see that at eta over S 12 over 4 pi, the big ENK code cannot run, and it stops evolving. So the code crashes out. Yeah. Yeah. And this is again, this is not a direct comparison. Uh, we're just comparing one first order hydro with the another first order hydro, varying eta over S, and just seeing that at what range, at what eta over S, our formulation is evolving smoothly without any problems. There's no comment on the big ENK. I mean, of course, it's eta over S over equal to 12 over 4 pi is outside the regime of the big ENK applicability, I think. So the code will most likely break down there. The equations of motion will most likely break down there. Because it seems one of the conclusions from the paper by Franz Picoris was that when you increase the eta over S, then the mean free path is almost equal to the system size. And then the evolution, the numerical evolution will incorporate the second order ingredient terms, which is apparently not present in the big ENK first order formulation. So it pushes the system out of the conversion. Yeah, sorry. So one can smooth this oscillate the sharp spikes if one uses the different discretization scheme, but the oscillations will still be there. I'm not sure what is the main physical reason behind these oscillations. I cannot say more than that. Why? Yeah. So yeah. Yes, of course. But yeah, beside that, I don't know what is the physical reason behind it. Maybe blue curve is Gensky frame, so there's no theta in pi. Okay, so this is the parameter for lambda and chi. Only for I mean, you can use some other values for lambda and chi to fix the frame, but once you fix the frame, then you compare it. So this is the fixing of the frame for lambda and chi. Of course, you can change this and then you compare again, but we haven't done it. We just fixed the value for lambda and chi, and then we solved it and compared it. Uh, I would say yes, because these are the values which have been used before for more numerical analysis. So I say we just use their values. Sorry. No, but this is around time which is 9 Fermi. So this is a snapshot of a evolution which is a 9 Fermi. So this is quite late, right? In the evolution of hydrodynamics. But okay, I don't know. I mean, means this is evolution. This yeah, right. And okay, so yeah, it's a free parameter. Yeah, so this is you can choose and you can fix a frame. So these are free parameters. Uh, yeah. So once you set these parameters, then you fix the frame. Yeah. So for the large equivalence, you see that there are some oscillations, and because of this causality, I mean, the big BDNK is developed such a way that the perturbations should strictly vanish outside of the causality edge. And since at this value, at this e cover S, this enforces a coordinate, I mean, the theta function in the coordinate space, and this gives rise the Gibbs oscillation in the computational domain. So that is why these oscillations are coming at, I mean, coming here in the numerical evolution. But however, for the Densky frame is increasingly dissipative in the ultraviolet regime. And about this non-causal behavior, you see that even after the causality edge, there are some traces of Densky frame evolution, which is present, but this is very negligible, meaning that if you compare two Lorentz boosted observers, and the discrepancy between two Lorentz boosted results are beyond the limit of hydrodynamics. So this is not a problem from the practical point of view. So this non-causality is not a serious issue if you have if the two Lorentz boosted results are beyond the applicability of hydrodynamics. If I understand your question correctly, you're saying that where do you find this Lorentz invariance breaking terms in density frame, and how do you find this Lorentz breaking? I mean, what was your question, Pavel? So we, within the regime of hydrodynamics, you will the differences between the Lorentz results are not there, so to speak. So you'll not see any difference between two Lorentz-Buschke results. Yes. Yeah, I'm not sure I can answer this question because whenever we see this numerically, I mean, numerically speaking, this Lorentz breaking terms have some discrepancy, but that is beyond what we can trust in hydrodynamics. Within hydrodynamics, you throw a higher order derivative terms, yes. Se sorry, what? But that will arise in the higher order terms, right? Uh, yeah, once, yeah, yes. So that is where I present the, the comparison between QCD kinetics, that is 1+1 gluon distribution, kinetics with a density frame. For 1+1 gluon distributions, I mean, it's a system of 1+1 system of only gluons. What do you mean? Right, Boltzmann equation, yeah. Using the Boltzmann equation. Yes, yes, yeah, yeah. Okay, right. It's a effective. What's the collision term? It's a RTA. Yeah, yes, yes. It's not very trivial, but it is doable. Yeah. So this is the comparison between Gensky frame and the 1+1 Kusiki kinetics with music for various value of eta over S, 2.3, 6.4, and 18.6. So as you were saying that the standard model for us is the Kusiki kinetics, and I would like to see where and how this formalism is breaking down. So for eta over S 2.3, you see that the Kusiki kinetics has a very nice agreement with both music and Gensky frame, which is this one, this blue, the second line. But for when you increase the eta over S, you see that the music, because it is a second order formalism, it has means is extra parameters, and these extra parameters are somehow helping music or MIS to have a comparison with the Kushigi kinetics, but second order transport coefficients are not present in density frame, and this discrepancy is, we think, is because of that. MIS, MIS, Mueller, Israel, Stewart. Yeah, right. So this discrepancy is mostly because coming because of the second order terms not present in density frame. For equivalence, which is much larger, where the mean free path becomes almost equal to the system size. So you see that both of them does not match the Kushigi kinetics in any way, but you see, I mean, the density frame have some some qualitative feature seemingly looking like Kushigi kinetics. But we're not claiming that this is the exact agreement. We are just saying that even for the eta where it's very small, it can match with the Kushigi kinetics, which is we wanted to see. Music or any other, yes, right. So this is not better than music or any other formalism for large Nusselt number, but I mean, this is a better alternative with respect to music in terms of the numerical complexity or the or computational complexity for small eta wires. Okay, so before I finish, I just this is the last part of my talk. So the point is we would like to use the Metropolis algorithm to model fluctuations. So how and why means this Metropolis works very nicely. I'll just give you one example. So this is the stochastic equation of motion for the Brownian particle, where eta is the drag force and noise, and the probability distribution evolves to equilibrium with respect, which is e raised to minus beta h. H is the free energy. One way to solve this thing is to use the operator splitting method, where you neglect the right hand side and solve a ideal step for the ideal that is called ideal step or symplectic step, and then following the symplectic step you do the Metropolis update. In the Metropolis update, you make a proposal for the right variance for the momentum, and the variance is fixed. This proposal, this momentum proposed update is fixed because of the fluctuation dissipation theorem. So once you fix the update, you make a proposal for the to have the to transfer between one fluid cell to the another fluid from one cell to another cell, and then you find the change in the free energy between two cells. So this proposal is accepted if the delta H, the change in free energy, is negative, or if the change in free energy is positive, you accept the proposed update with the probability guess. So yeah, but this is I'm talking about just I mean Brownian motion. How one can solve the Brownian motion using the Metropolis algorithm. But why there is a question of non? Right. So what is the I'll come to that. I'll come to that. Why Metropolis is important here, I'll come to it. I'm just let me just complete this part that in the Metropolis means in the Metropolis algorithm, once the proposal is accepted, then you calculate the mean of the accepted proposals, and that mean will reproduce the dissipative terms, and the variance will give you the noise. So this is the main point here. Mm. Fluctuation by hand. I'll come to that. I'll come to that. So, okay, so let me just clear it. So in the Metropolis algorithm, you propose an update, you find the mean of the accepted proposals, and that mean will give you the dissipative terms. Why this is important is that in the Gensky frame hydrodynamics, we have the dissipative terms, and that automatically comes out from the Metropolis algorithm, which is why we are interested in Gensky frame. So numerically speaking, you only have to do an idle step to solve the Gensky frame hydrodynamics, and then do a Metropolis step. And that Metropolis will automatically give you the dissipative terms in the hydrodynamics. Yes, simultaneously giving the dissipative terms and the noise using this for the Gensky frame. So that is the primary motivation. Okay. So the primary goal was to use Metropolis for us, but we haven't been able to do it for the MIS or any other formalism. That's why we came across this formalism, Gensky frame hydrodynamics, and we see that this naturally can be coupled together with the Metropolis algorithm. So that is, I think, the advantage of Gensky frame hydrodynamics. That this comes out beautifully. So these are the Metropolis steps are guaranteed to converge to the required distribution function. Metropolis naturally reproduce the Langevin dynamics, detailed balance and fluctuation dissipation theorem are automatically preserved, and it has been used for many other problems. Thomas Sheffer given a very nice overview of this Metropolis algorithm on 5th May. Please have a look. So for the diffusion equation, even for a simple diffusion equation, this can be used, and this is the stochastic equation of motion, the free energy, which is given in terms of charge density and susceptibility. You make a proposal for the charge transfer to move from A to B, like this, and then you can put the change in entropy. This change in entropy is nothing but the change in chemical potential between the fluid cells, and this proposed update, which is this one, is accepted with probability this. Then the mean of the accepted proposals reproduce a dissipation term, and the variance will give you the noise. So this dissipative terms will automatically comes from the Metropolis algorithm. Finally, for the stochastic density frame relativistic diffusion equation, again, you do a charge transfer with the transverse, with the proper transverse and longitudinal invariance, longitudinal variances, and then after doing the accept reject, according to a change in the sign of entropy, it will give you the dissipative terms and also give you in addition the noise. So this Metropolis algorithm is actually very nice to model the fluctuations once you know how to use this, and which hydrodynamic formalism is able to naturally couple to this Metropolis algorithm is kind of difficult to find, but thanks to Armour and Zhang, we have this Gensky frame hydrodynamics, and Metropolis algorithm works naturally with the Gensky frame hydrodynamics here. It is fixed by the fluctuation dissipation theorem. So okay, let me Okay, so this is just the Brownian motion, stochastic equation of motion, and this noise correlation function is this 2 key eta delta t key. Yeah. So this that update is actually proportional to this 2 key eta. So this is my update, which is this here. Sorry, this one. No, it's not arbitrary. As I say, it is fixed by the fluctuation dissipation theorem. So once you know what is your noise correlation for your system, for example, Brownian motion, then this is fixed. No, it's not. I mean, what distribution we're talking about? Oh, no, yeah, it is not arbitrary. It is fixed. It's fixed. Yeah, Gaussian. Gaussian. Yeah. 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 And this is a Gaussian. The distribution is a Gaussian with, I mean, as you said, it's a non-zero delta p. Yeah. I mean, well, it's not zero. Sorry. I fixed this. I fixed this delta p, which is so. This is my the proposal for this transfer of momentum, and this is the random number. So the variance of this random number is 1. So this is my proposed update. Mean value is this. Yeah, right. Yeah, okay. Yeah, so even for a Gensky frame, relativistic diffusion equation, this can be implemented. You just have to propose a charge transfer with the proper update for the transverse variance and the longitudinal variance, and then you do the accept reject according to the change in signing entropy, and that will give you the mean diffusive current and the variance, the proper correct variance. Just an example. That was just you mean this? So this is non-relativistic diffusion equation. Non-relativistic diffusion equation. This is just like so. So there are two examples. One example is a Brownian motion, which was before. How to, no, it's not. Right, right. Origin of KMS? Probably, I am not very sure. Probably. I don't know. Right. I don't know there's a direct link between this algorithm or KMS. I'm not familiar. Yeah. Yeah. So as finally, I'm going to say that this works very nicely with density frame hydrodynamics, and this is the this is the best way to simulate to model noise, the stochastic noise into the hydrodynamics, and we are also working on that, developing the code for this. In summary, so this is stable, density frame hydrodynamics stable, first order in time, no non-hydrodynamic modes. The Metropolis algorithm will give you the noise and dissipation directly. The procedure is to take an ideal scape, make a random momentum transfer with the specific variance that is fixed by the fluctuation dissipation theorem. We have generalized this Metropolis procedure for the full hydro in the Bayesian and general coordinates. There are no simulations yet for the full hydro noise, but we are working on that. And this has a good agreement with the relativistic MIS and BDNK for the small specific shear viscosity, and maybe works better or similar to MIS for the larger shear viscosities. This is again debatable. The momentum proposal is parallel transport from the cell face to cell centers. If you go to a general coordinates, then the Metropolis, for the Metropolis algorithm, this procedure has to be incorporated. The transfer is parallel transport from the cell face to cell centers, and that will give you the covariant derivatives to the dissipative strain. Thank you. There is no, there is no. I think yeah, in his paper they have done this. If I'm not wrong, I think you have in your paper there's a last section which is doing the linearized analysis for this. Right? So just coming to, I mean, just an added line on this. So, so Lorentz symmetry can presumably be restored if, as he said, that if you have non-hydrodynamic modes, or you have to incorporate all the infinite order of terms in your theory in the K-mu. So either way, you can restore the causality, the Lorentz symmetry. So this was the proof given here in this paper. So either you need to incorporate the non-hydrodynamic modes, or you need to incorporate the higher order, all higher order terms. Yes, yes. So stable and causal, that is. So yeah, and this is the first theory without any gapped modes. So which is making it non-causal. Yeah, then it will. No, no. At least we have seen for the diffusion equation, you can restore the Lorentz symmetry, the causal. Yeah, yeah, we have done this using the resummation techniques in the first paper. You can see that at least for the diffusion equation, you can go, that causality can be restored if you include all the higher order terms. Yeah. So we compared, we compared all the terms, not all the terms, but we incorporated terms order by order, and then we see the plots. We see numerically that it goes towards the causality. Yes. No, no. What we are saying is that this is a non-causal first order theory with only hydrodynamic modes. So to restore causality, either you need gapped modes or non-hydrodynamic modes, or your theory has to have all infinite order terms. Right. Right. Uh, okay. So this dispersion relation is consistent with the causality constraint which was which was given in the paper by Spalensky and Heller, that if the imaginary part of omega is right, 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 right. So So when I said that Lorentz symmetry can be rescored, I meant that this condition, imaginary work of omega less than this k, is not violated. That is not violated. That is, yeah, in a special 1+1 covariant kinetic model, that you can, there you can do it analytically. I can show you the calculations. Right. For full hydro, I don't really know right now how to do this, how to restore the causality. Means by incorporating infinite order of terms. But one has, we need to see. And there is a possibility, as I said before, that you can restore the causality, but we just did it for this diffusion equation. But the full hydrodynamics we have to see. We have to we have to see. Yes, yes. Effect or what is the value? This one. This is like 0.15. The Nusselt number will be 0.15. This will be around 1. Yeah, that is, I think, predictable, right?